Exercise 6 of chapter 8 is coming back to my favorite rule in all of linear algebra, which is called the live evil rule. And as a reminder, the live evil rule is basically about applying a transformation to a set of matrix products. And where live evil comes in is that live evil is a palindrome. So it's spelled the same way forwards and backwards. And evil is live spelled backwards. So to apply a transformation to each of the individual matrices in the product, you need to apply that transformation to each matrix and then reverse the order. So you saw that previously in the book with the transpose operation. And here we are going to explore this using the inverse of matrix multiplication. So what you want to do here is create two square full rank invertible matrices A and B, and then compare using Euclidean distance the inverse of the product AB, and then A inverse times B inverse and B inverse times A inverse. And then here I write, before you start to code, make a prediction about which results will be equal. Now, based on everything you learned about the live evil rule in this chapter and in previous chapters, we should expect that number 1, so result 1 and result 3 are equal, and result 2 is going to be different. Now, that is not necessarily a trivial result. We might also find that 2 is equal to 1 and 3, and that could happen for some special matrices. For example, if A is the identity matrix, then we would expect 2 and 3, and therefore also 2 and 1, to be the same as each other. But assuming that A and B are just random numbers matrices, then we do expect 1 and 3 to be the same, but 2 to be different, and that's because we are not appropriately swapping the order of these matrices. Okay, so we compute Euclidean distance and then print out the results like this. Here is where I create the two matrices. You can see these are both square matrices. Now, the code is set up here, so it's fairly straightforward for you to change these from square matrices to non-square matrices, but I don't recommend doing that just yet because that is basically the goal of the next exercise. Okay, so here I have option 1, and that is the inverse of A times B. Here we have option 2, that's the inverse of A times the inverse of B. And again, it feels intuitive. When you're new to linear algebra, it's intuitive that these two should be the same. But yeah, it's not that simple. And it turns out that option 3 turns out to be the right answer. So the inverse of B, which is the second matrix, times the inverse of A, which is the first matrix here. Okay, and then here I'm computing the Euclidean distances. You can see that I subtract the two matrices and then square that difference matrix and then sum up all of those elements. And here I'm not specifying an axis along which to sum. So this is going to sum all of the elements in the entire matrix. And then I take the square root of that sum. Okay, so let's see what the results are. Here we see that the distance between AB and that quantity inverse and A inverse times B inverse is 13. And now it doesn't actually matter what this number is because they're all random matrices. So these are not interpretable numerical values, but the key is that this is definitely not 0. And that's what you see here. So AB inverse and B inverse times A inverse, those distances are actually 0. Now, I haven't written the code here to expand this to multiple matrices, but I encourage you to do this. It's not very difficult. All you need to do is add another random matrix here, and then this is going to be A times B times C. And then here I will write, then let me see, this should be like this. I guess, I said I wouldn't do it, but I'm so far into doing it now, I might as well continue. Okay, so here we have option 3 is C inverse times B inverse times A inverse. And here I'm going to set option 2 to be A inverse times B inverse times C inverse. And now that needs to be capital C like that. Now, of course, there's more options as well because we have three matrices. So you could do A inverse times C inverse times B inverse, but I mean, that makes even less sense. Again, there are going to be random, specific matrices where this actually does work. For example, if all three of these is the identity matrix, and it's trivial that this is going to work. Okay, let's see. And so basically here we can confirm again that, okay, now this text I didn't update yet, so this is wrong. You can ignore this, but we can see that this result, option 2, when we keep the order the same, this is incorrect. And option 3, when we reverse the order, is that actually is correct.